The exponential family is a large and important class of probability distributions. Many distributions we use in statistics belong to this family. The general form is f of x given eta equals h of x times exp of eta transpose t of x minus a of eta. Let us explain the parts. H of x is called the base measure. It depends on the data, but not on the parameter eta. Eta is the natural parameter. T of x is the sufficient statistic. A of eta is the log normalizer or log partition function. Its job is to make sure the density integrates to 1 or the probability mass function sums to 1. This form is important because it makes sufficiency clear. For an IID sample, the sufficient statistic is usually the sum of the individual statistics. Tn equals sum from I equals 1 to n of t of xi. The log normalizer also gives moments. In many exponential family models, e of t of x equals the gradient of a of eta, and var of t of x equals the second derivative or Hessian of a of eta. This is one reason the exponential family is so useful in theory and in machine learning. Okay, now let's write some familiar distributions in exponential family form. Start with Bernoulli distribution. The Bernoulli probability mass function is p to the x times 1 minus p to the 1 minus x. We can rewrite it as exp of x times log p over 1 minus p plus log of 1 minus p. The natural parameter is eta equals log of p over 1 minus p. This is called the logit. The sufficient statistic is t of x equals x. The log normalizer is a of eta equals log of 1 plus e to the eta. For the Poisson distribution, p of x equals x equals x is e to the minus lambda times lambda to the x divided by x factorial. We can rewrite it as 1 over x factorial times exp of x log lambda minus lambda. Here eta equals log lambda. T of x equals x. A of eta equals e to the eta. And h of x equals 1 over x factorial. For the normal distribution with known sigma and sigma squared and unknown mu, it can also be written in exponential family form. The natural parameter is eta equals mu divided by sigma squared, and the sufficient statistic is t of x equals x. For a sample, the sufficient statistic becomes sum xi. These examples show why exponential families are closely connected to simple sufficient statistics and conjugate priors. Okay, in a Bayesian estimation, the parameter theta is treated as uncertain. Before seeing the data, we describe our belief about theta using a prior distribution, pi of theta. The data provide information through the likelihood L of theta given x. After observing the data, we combine the prior and likelihood to get the posterior distribution. The posterior formula is pi of theta given x equals L of theta given x times pi of theta divided by the integral of L of u given x times pi of u dau. The denominator is the normalizing constant. It makes the posterior integrate to 1. If theta is discrete, we replace the integral by a sum. The short form is posterior is proportional to likelihood times prior. This is the Bayesian version of Bayes' theorem. The prior represents information before the data. The likelihood represents information from the data. The posterior represents updated belief after the data. This is different from MLE. In MLE, theta is fixed, and we choose the value that maximizes the likelihood. In Bayesian estimation, theta has a distribution, and uncertainty about theta is described by the posterior. Okay, let's talk about conjugate priors. A conjugate prior is a prior that gives a posterior in the same family as the prior. This makes a Bayesian updating easy because the posterior has a known form. For the binomial model, if x given p is a binomial with parameters n and p, and the prior is p distributed as beta alpha beta, then the posterior is p given x distributed as beta alpha plus x, beta plus n minus x. This means we add observed successes to alpha and observed failures to beta. This is prior and this is posterior. For IID Bernoulli observations, the same idea applies. If S equals some xi, then the posterior is beta alpha plus s, beta plus n minus s. For the Poisson model, if xi given lambda is Poisson and the prior is gamma alpha beta, using beta as the rate parameter, then the posterior is gamma alpha plus some xi beta plus n. For a normal model with known variance and unknown mean, a normal prior on the mean gives a normal posterior. The exact formula uses a weighted average of the prior mean and the sample mean. The weights depend on prior precision and data precision. The main idea is simple. Conjugacy lets us update parameters by adding information from the data to information from the prior. Okay, let us derive the beta binomial update. Suppose x given p follows a binomial distribution with n trials and successes probability p. The likelihood is proportional to p to the x times 1 minus p to the n minus x. Now choose a beta prior. P is distributed as beta alpha beta. The prior density is proportional to p to the alpha minus 1 times 1 minus p to the beta minus 1. The posterior is proportional to likelihood times prior, so pi of p given x is proportional to p to the x times 1 minus p to the n minus x multiplied by p to the alpha minus 1 times 1 minus p to the beta minus 1. Combine powers of p and 1 minus p. We get p to the alpha plus x minus 1 times 1 minus p to the beta plus n minus x minus 1. This is the kernel of a beta distribution. Therefore, p given x follows beta alpha plus x, beta plus n times x. The posterior mean is alpha plus x divided by alpha plus beta plus n. The MAP estimate is alpha plus x minus 1 divided by alpha plus beta plus n minus 2 when the parameters are greater than 1. Interpretation is very useful. Alpha acts like prior successes and beta acts like prior failures. The data simply add real successes and failures to these prior counts. Now let us derive the gamma Poisson update. Suppose x1 to xn are IID Poisson with rate lambda. The likelihood is proportional to e to the minus n lambda times lambda to the sum xi. We choose a gamma prior for lambda with shape alpha and rate beta. The gamma prior density is proportional to lambda to the alpha minus 1 times to the minus beta lambda. The posterior is proportional to the likelihood times the prior, multiply the powers and exponentials. We get lambda to the alpha plus sum xi minus 1 times e to the minus beta plus n times lambda. This is the kernel of a gamma distribution. Therefore, lambda given x follows gamma with shape alpha plus sum xi and rate beta plus n. The posterior mean is alpha plus sum xi divided by beta plus n. The MAP estimate is alpha plus sum xi minus 1 divided by beta plus n if the shape is greater than 1. The interpretation is also simple. The prior shape alpha contributes prior event counts and beta contributes prior exposure or time scale. The data at the observed event count sum xi and the sample size n. Be careful with parameterization. Here beta is a rate, not a scale. If a book uses a scale instead of rate, the formula looks different. MAP means maximum posteriori estimation. It chooses the value of theta that maximizes the posterior distribution. The formula is theta that theta hat map or MAP equals argmax over theta of pi of theta given x. Since the denominator of the posterior does not depend on theta, this is the same as maximizing log likelihood plus log prior. So theta hat MAP equals argmax of log L of theta plus log pi of theta. MLE uses only the likelihood. It is theta hat MLE equals argmax of log L of theta. MAP use both the likelihood and the prior. If the prior is a uniform over the parameter space, then the log prior is constant and MAP and MLE are the same. MAP is useful when data are limited or when we want to include prior knowledge. In machine learning, MAP often looks like a regularization. Maximizing log likelihood plus log prior is the same as maximizing log likelihood minus a penalty term. For example, a Gaussian prior often leads to L2 regularization. But remember, MAP is still only a point estimation. It does not show the full uncertainty in theta. The full Bayesian answer is the posterior distribution, not only its mode. Okay, let's talk about decision theory for estimation. In decision theory, we ask, what does it mean for an estimate to be best? To answer this, we must define a loss function L of theta and measure and A measures the cost of choosing estimate A when the true parameter is theta. The frequent risk is R of theta and delta equals E theta of L of theta and delta of X. This means the average loss when the true parameter is theta and the estimator is delta. The base risk averages the risk over the prior distribution. It is R of pi and delta equals the integral of R of theta and delta times pi of theta d theta. Different loss functions give different base estimators. Under squared error loss, L equals theta minus A squared. The base estimator is the posterior mean E of theta given X. Under absolute error loss, L equals absolute value of theta minus A. The base estimator is the posterior median. Under 0, 1 loss, the base estimator is the posterior mode, which is the MAP estimate. So the best estimate is not defined until we say what loss function we care about. If large errors are very costly, a squared loss may be reasonable. If we want a robustness, absolute loss function may be better. If we only care about choosing the most likely value, MAP is appropriate. This slide gives a template for solving estimation problems. First, write the model. Always start with f of x given theta and the parameter space capital theta. Without the model, the rest of the solution is not clear. Second, write the likelihood. If the sample is IID, write L of theta as the product of f of xi given theta, then write the log likelihood as a sum. Third, find MLE or MAP. For MLE, maximize the log likelihood. For MAP, maximize log likelihood plus log prior. Use derivatives, check boundary points, and confirm the maximum. Fourth, study estimator quality, compute or discuss bias, variance, MSE, consistency, Fisher information, and approximate standard errors. This tells us how reliable the estimate is. Fifth, look for sufficient statistics. If a statistic is sufficient, we can compress the sample without losing information about theta. This can simplify both theory and computation. So the full workflow is model, likelihood, estimator, uncertainty, and interpretation. This structure works for almost every estimation problem in the course. Okay, let me summarize the main ideas from today. First, likelihood is the probability model viewed as a function of the unknown parameter after the data are observed. Second, maximum likelihood estimation chooses the parameter value that maximizes the likelihood or log likelihood. Third, the score equation is often the main calculation. Set the derivative of the log likelihood equal to 0. Fourth, estimator quality is not only about getting one number, we must also think about bias, variance, MSE, consistency, and efficiency. Fifth, Fisher information tells us how sharply the likelihood identifies the parameter. More information usually means a lower uncertainty. Six, a sufficient statistic is a summary that preserves all information in the data about the parameter. The factorization theorem is the main tool for finding sufficient statistics. Seventh, the exponential family gives a general form that includes many useful distributions and naturally reveals sufficient statistics. And finally, Bayesian estimation combines prior and likelihood to form the posterior. MAP is the map, or MAP is the posterior mode. Under squared loss, the best Bayesian estimate is the posterior mean. Under absolute loss, it is the posterior median. Under 0-1 loss, it is the map or MAP estimate. Okay, these exercises help you practice the relationships from today's lecture. For the first exercise, suppose xi follows Bernoulli p. Show that p hat equals x bar is unbiased and var of p hat equals this term. In this regard, start with e of x bar equals 1 over n times sum e of xi. Since e of xi equals p, e of x bar equals p. Then compute var of x bar. Because the xi are independent, var of x bar equals 1 over n squared times sum var of xi. Since var of xi equals p times 1 minus p, the final answer is p times 1 minus p divided by n. For the second exercise, suppose xi follows Poisson lambda. Derive the MLE and compute Fisher information. You should get lambda hat equals x bar. The score is minus n plus sum xi over lambda. The second derivative is minus sum xi over lambda squared. The Fisher information for n observations is n divided by lambda. For the third exercise, you can use the exponential density f of x given lambda equals lambda e to the minus lambda x. The likelihood is lambda to the n times e to the minus lambda sum xi. The log likelihood is n log lambda minus lambda sum xi. The derivative is n over lambda minus sum xi. Therefore, lambda hat equals n divided by sum xi, which is 1 over x bar. For the fourth exercise, use the factorization theorem to prove that sum xi is sufficient for Poisson lambda. For the fifth exercise, if x equals 7 successes out of 10 and the prior is beta 2, the posterior is beta 9, 5. The posterior mean is 9 over 14. The MAP or map is 8 over 12 or 2/3. For the last exercise, prove that under squared loss, the base estimator is E of theta given x. The trick is to expand E of theta minus a squared given x and minimize with respect to a. Okay, for further reading, Ross' Introduction to Probability Models is a good main reference for probability models. Casella and Berger Statistical Inference is a strong reference for estimation theory, likelihood, sufficient statistics, and unbiased estimation. Thus, Gupta Probability for Statistics and Machine learning connects probability and inference to machine learning. Robert and Casella Monte Carlo statistical methods will be useful later when we study simulation and MC. In the next section, we start Markov processes and Markov chains. The main idea will be the Markov property. The future depends on the present state, not on the full past history. In formula form, p of x n plus 1 equals j given x n equals I, and the past equals p of x n plus 1 equals j given x n equals I. We will study transition matrices, Chapman-Kolmogorov equations, recurrent and transient states, stationary distributions, and stopping times will be studied in the next sections. Please review today's estimation formula because likelihood, posterior ideas, and Markov models will connect again later in the course.